Yeah, something's still wrong. I can't get that projector thing to work, so. I just sent an email to them, but let's see, so let's see, I didn't, so I didn't put the I didn't grade the homework yet, but anyway, so I haven't gotten to that, but I put the new homework 4 up here. I'll talk about it tomorrow. It's about a conjugated polymer thing. So it's a little involved. Anyway, so this have things up, but let's see now. So I'm just going to go through some of the slide things today. Any questions, anything that you go through? All right. So yeah, last time I went through this business of getting this short range interaction, like the simplest kind, and then just from no back step, you get this increase of the Kuhn length by 1.5. So, but this chain scaling remains the same. It's still Gaussian. So anyway, so there's a bunch of different things that can change the persistence length. So like the two that Flory looked at were bond angle restriction, bond rotation restriction. Then there's these issues of steric interaction, like side groups on the chain, tecticity, conjugation. So we'll look more at that in the homework this week. And then main chain aromatics, that's kind of in the homework too. And then charges on the side of the chain. So I'll talk about that at maybe next week, I guess. And then hydrogen bonding can change. So like in proteins, you get hydrogen bonding that shifts the persistence and helicities and impact. There's probably other things. So it's kind of a list. And then I said, like, you can a measure of the chain stiffness, this characteristic ratio that also came from Flory's. This is all from like 1960s, Flory's first book, the characteristic ratio. So they were looking for ways to talk about these two effects, like this kind of local rigidity of the chain and this idea that the chain has excluded volume, right? So he wanted some number that would give that to you. So this short range interaction number is this characteristic ratio. And then the other number is the coil expansion factor. They both talk about how the chain gets larger. So with this rigidity factor, the chain gets larger because the steps get longer and the number of steps gets smaller. And then with the chain scaling changes, so it expands. Right. So we have the infinity, which is the Kuhn length over the chemical length. Right. We had and then the coil, that's called the characteristic ratio. The infinity means the molecular weight is infinity. So I'll show you why that's the case. And the other thing is called the coil expansion factor. So this is short range interaction. With the long range interaction, you have the coil expansion factor, which is usually called alpha, and that's like R into the end distance squared over like R ideal like chemical unit and end distance. So that one's a N chem L chem squared, and this thing, the other thing is like N Kuhn The other thing is going to be a different scaling. So that this is just a number. This is measured. This is not. It's not going to be a Gaussian. It's not going to be. The power of L is going to be 2 here. Or it's going to be a different dependence, like R squared. So R is going to depend on the mass, either 1 by whatever the fractal dimension is. So here, it's R squared goes with N, but for this case, it's going to be R goes with some other dimension. Like, in other words, an expanded coil isn't a 2-dimensional. We'll talk about that later. But that's the long range interaction part, right? So, but there are these, so the idea is that these 2 paired terms that both talk about how the coil expands from a random walk, right? And you wanted to quantify that in the context of splitting it into these 2 effects, like a local rigidity and a long range change in the shape of the chain, the way the scaling of it. Okay, so that's kind of the idea of this. So this falls into the realm of the local effects, and usually, so people will tabulate this number. So it's just like if you remove the bond length, could be different for different materials, like PEO. PEO is this this guy, polyethylene oxide. It's also poly what is it? PGA or something, polyglycemic acid, right? So there's kind of 2 names for that. And if you take so ethylene oxide is water soluble, and then methylene or propylene oxide, let's see, ethylene oxide should be 2 CHs in here. And then propylene oxide is like 3 of these. Just like that. It's not water soluble. So you can make a block copolymer. Let's say that one's blue and that one's black. So you can make a block copolymer where you have PEO, PPO. And you can tune the water solubility of it. So that becomes like, wait, this PEO, say with another carbon here, all right. That becomes like a building block for all the biopolymers. Like everything's going to be PEO. If you want to make a soluble particle, you stick PEO chains on the surface of it, for instance. And this polymer, so it'll go into water room temperature. If you heat it to 60 degrees C, it phase separates. So it phase separates on heating. So it'll cloud up if you heat it up. So use it for something like cancer cells are hot. So you can use it as like a way to dump drugs. So it'll be soluble in your blood, and then it gets to the hot cancer cell and dumps off its load. So it's got a lot of functionality. One of them, like this, if you combine these 2 in a block copolymer, that's called a pluronic. The commercial name. So that's what's like a hand sanitizer is a pluronic with ethanol and some water, like 70% ethanol, and then you put a pluronic and it makes a gel, because there's a partial solubility of this part, so it phase separates out and makes a network. You end up with a gel, swollen gel, and then basically the residual goo that's on your hand after the hand sanitizer is this pluronic stuff, which is supposedly non-toxic. I mean, it's pretty much non-toxic. In other words, they use this so much in medical that they know the impact of it is kind of 0. Anyway, so that's got a pretty low, because the oxygen bond is much more flexible than the carbon bond. So you put an oxygen bond on the main chain, you get a lower C infinity. Ethylene is like your standard number 7. It's kind of 7 carbon bonds to make a Kuhn step. Then styrene, because it's got an aromatic on the side. It's just polystyrene has, think about the oops. I don't want the H's, they put the aromatic group on the side. So the thing's sterically interfering and makes the step lengths longer. So you get 10 instead of 7. Anyway, so and we found like these small changes end up to be big changes if you look at the, say, the overlap concentration, like the density of one within one coil. So the coil's flying around with a density of its own, that's the overlap concentration. So even if there's no back step, so 1.5 characteristic ratio. So this number times the step length would be the characteristic ratio. 1.5 gives you 1/3 or 3 times 1/3 of the overlap concentration. So you can imagine that if it was 7, that's a significantly different overlap concentration than if it was just carbon-carbon bonds. Like,
What is it overlap concentration?
so it's say the chain is going around, it's got solvent, it's in a solution, it's got solvent in it, right? So what's the concentration in the chain? So it's the mass of the chain times the size cubed, divided by the size cubed. When the solution reaches that concentration, all the little balloons of chains touch each other, so they overlap. So that's the point where you're going to get, you can't, for analytic techniques, you can't see the size of the coil anymore because they're overlapped. So it's just a mesh. It's like a fleece. You can't see the fibers. Right. So this is well above the overlap concentration. Below, you would see individual fibers floating around my body, which wouldn't be a coat, you know. So it'd be anyway. So anyway, so that would be a gel. Like the pluronic in the hand sanitizer is a gel. That's why you can use it. It's because over its overlap concentration. It's above its overlap concentration. So all the properties you want of like a liquid polymer mixture are going to be like above the overlap. But if you want to study it analytically, want to see a single chain, you have to be below that. So you need to know that magic number. And that's going to depend on the Kuhn length. Right. So, and it's going to severely depend on it, much more than the Kuhn length changes by 1.5, which seems like a lot. This is like a 3 times as much, right? So it's significantly more. So basically, you could figure that out for the 6.7, it would be like 100th or something. So it's a much, much lower overlap concentration for that. So anyway, so this is the other thing that's weird. Okay, so in a computer simulation, so this is Monte Carlo simulations, which I haven't talked about yet, I think. Let's see. I'm pretty sure both these papers I'm going to show are like Monte Carlo simulations, but so we'll talk about that later on. But basically, you can take so it's similar to the so this is a spring. The spring modulus is 3 kT over NL squared. Generally, right? So you have things, so you have the distance between the bonds, and they're gonna go with like this 3 kT over NL squared as the modulus, and then the delta R thing. Right. So space, that's the spring constant. And then you can just run so either do molecular dynamics and let it shake and bake, or you can like do Monte Carlo, which is a little bit different. It's a different algorithm. So I'll talk about that after. But basically, let it cook for a while, and then you can, because you have position of each bead of the chain, right? You can say like, from this bead, I'm gonna figure out like how far it goes before it changes, say, an angle of like 6 degrees. Right? And then I could say that that distance might be something like the persistence length. And I'll show you how you get that a number of an angle like that. But basically, you could imagine, just say like how far do I go before it deviates? So that's my persistence. So you can get a number for this C infinity or LK for each bead, including like the first bead, right? So you can map LK or LP. He calls it LPK. It's actually persistence he's getting. And this method is kind of persistence method. I'll show you after, but so he's measuring the persistence as functionally starts at bead 0. He's going to make a 47 bead chain. And then he's going to vary the spring constant. So this is his spring constant between this is like I think lambda is like a bending constant. So there's a spring constant. This is 3 kT over NL squared from last homework. There's also like an angular kind of spring constant. There's some kind of spring constant, K theta, that's times cos of the angle will give you like the force of bending the spring in a computer simulation, right? So So you can plug in like whatever, he calls it here lambda, right? So it's a spring constant for bending the angle. Estimates in there, but. All right, so he's got the bending completely flexible 0, and then 10 like really stiff, and the 10, the stiff one is this top one. So you can see there's a dependence, so that there isn't one persistence length for a chain. That's the point. Unless you have a really stiff chain. Let's see. Unless you have a completely flexible chain, then you get just a one persistence length, but still at the end, like this persistence length drops. You know, there is a plateau value for some chains, but basically depending on the stiffness of the chain, it might never plateau. See, so the value you measure of persistence length isn't something you could think about as an analytic number at that point. Like it's a moving target. If you make the chain longer, it will be a different. Anyway, for all of them, it's going to have a molecular weight dependence, right? So this kind of muddles the waters. You had a nice little analytic number. You had the coil size. You had NL squared. You have this thing. It's a parameter that describes the chain. So you can say, oh, if I chemically modify and stick an aromatic ring on, it makes it stiffer. And I can just talk about that. But lo and behold, it isn't even a fixed number. Like you can't. So if I make the molecular weight longer and longer, this kind of end effect diminishes importance. So in order to get the actual number of the plateau of this thing, then you want to go to infinity. Like you want to have no, so that the ends are totally diluted as much as they could be. So that's why they call C infinity would be like this kind of like physical limit of what this step length could be, right? So you have to kind of be careful when people are talking about the step length. You have to look at the molecular weight that they're looking at, right? Like for instance, in this paper this week, so they do a density functional. So density functional theory is something like inorganic metallurgy and ceramics people use to look at the electronic density around an atom. And then you can say like the semiconductor properties, the band gap and things from it, right? So it's kind of a weird, like LAMMPS is a free software and it's all like open source and it's shared and everything. And density functional theory isn't. You have to pay like $150,000 to get the program. And all it is like you have if you took chemistry, I guess they go through molecular orbitals and calculate the orbitals with quantum mechanics. Anyway, so you can only do that for really simple things. So you have like cheats to get around that, so you can predict the electron orbitals for other things, like for instance, for a conductive polymer chain, and you want to know the kind of what's going on with the bond angles within the chain, say, as a function of the energy, electron density in it. So this density functional theory program, you pay 150, 200K, find someone that knows how to run it, and then they'll give you that. They'll give you how the angles work in the chain. Anyway, so you can do that, and then you can add that up, and so you can get a persistence length from that. So you can take those density functionals. So you can't have kind of these spring constants from DFT, and then you can plug that into like a LAMMPS program or a Monte Carlo. Then you could let it shake and bake with KT, and then see what kind of persistence length you get out of it for short little chunks of chain. So that's then in the paper we're doing this week, they do that. Okay, but the problem is, if you have a plot like this, so what exactly are you measuring if you have like a 2 mer unit or a 1 mer unit or a 3 mer unit item, right? I mean, you aren't getting enough chain to see, it's all end, right? In the end thing, I mean, you can think about this end effect like a dog tail wagging, you know? So they have your chain going like that, and then these end things are like kind of wagging. They're a lot more flexible because they aren't tethered. So this part's like tethered by the two pieces. Over here, there's only one tether. So it's like a whip flapping around in the wind. The KT is the wind moving it, right? So anyway, this is the effect of a dog wagging his tail. And this is the body of the dog in the middle. That's the idea of this, right? So then the longer the dog and the stiffer the dog. Okay, so more flexible the dog, you reach a plateau, but it's lower. The stiffer the dog, I guess the wagging thing, anyway, maybe the dog thing falls apart at some point, but yeah.
And the bond angle of maybe silicon has have an effect on characteristic ratio.
Yeah, yeah, I mean, that's the point, like so you can do a, right, so the Flory did, that's what Flory did, so Flory did, so Flory is gonna take like you can have a freely rotating chain like that, so you fix this angle to be 109 degrees, and then you allow it to freely rotate about that, so that's the bond angle, right? And there's also a rotational isomeric state issue of this thing. So if you fix the bond angle, then you're going to get this Newman projection of the energy, and you can use that as a weighting factor for the or if you just or the Newman, this would be for the rotational states, right? You'd have an energy plot, so it'd be a probability function for the rotation. But if you just fix the bond angle, so instead of what we had this thing like we had what that we had this function, right? The b squared divided by that thing. If we just say no back step, that's our kind of our probability interference of the thing, which would have just been anyway, this would have been 0 for when I doesn't equal j, and 1. This would have been 1 when I equals j. But for the case where you have no back step, we have that thing, and then you can plug that into the double sum to get r squared, go through a little bit of math. So basically this sum function times b squared is this r dot r. When you have a bond angle restriction, that function is this cosine of your 109 degrees, or cosine of 1 minus 109, which is like 72, I think, 71, I guess. Right, so it's basically cosine of that 71 replaces this thing. You plug it into the same equation, this double sum, use this sum of geometric progression to solve it, and then you find out that you'll get the same answer, except instead of our simple little 1 over z whatever function, get this thing that involves the bond angle. The tau would be the 109. So I think that's 71 degrees for carbon-carbon, right? So it's just exactly the same thing as saying no backstop, except it's looks more complicated because it's got cosines in it instead of just the no backstep thing. The math is exactly the same double sum, and you end up with kind of the same answer, right? So everything you do can be framed up into that, in any kind of thing where it's an analytic thing that you're talking about, can be framed up in this way. So what Flory did was he said, all right, so this double sum has like I and j. So you have 2 points that you're considering and bigger distances between them. So that's a double sum is really like a matrix. So you can figure out for each one. So we're doing like powers of 1 over z minus 1 for the one case, and then powers of this cosine thing for the other. So basically you get a matrix of whatever factor you're putting in, which could be the angle, or it could be this potential, rotational potential. So it's gonna end up being matrix math. It's gonna be like multiplying matrices to get the effects of all these different things. So Flory's second book is all like just an essay in like matrix math, like 500 pages of just like this matrix times that matrix gives you like so you get all those things you can add up mathematically. You know, some things are kind of more complicated than that, but these are pretty simple algebraic functions with the potential for the rotational energy. So basically, you can do it. You know, I mean, you don't want to do it if you don't have to, and you don't have to, so don't do it. Basically, his book. I mean, if you like matrix math, I suggest reading his second book, because that's all it is. You know, it's like multiplication of matrices to end up getting this end-to-end distance thing, right? But all right. So there is a little story to go with this. All right. So Flory was fluent in Russian somehow, and I have no idea why, but I'm learning Chinese, so maybe it's like when you have an enemy, you learn their language and there's some kind of angle. So anyway, at the time during the Cold War, Russia had a whole separate polymer thing going on, and then the US had a polymer thing going on. And like, I think 5 years before Flory published his second book, a guy named Wolkenstein published a book in Russian in Russia, which was never translated into English, which was the exact book that Flory's second book was. Okay, so you'd think that this Wolkenstein guy would be upset about that. Anyway, so Wolkenstein, in fact, the Flory Florey-Huggins equation for solution theory in Russia, they call the Wolkenstein equation. So it's more than just this, it's more than just this matrix math thing. There's a bunch of things that were like, you couldn't tell whether it was done in the East or the West, you know? So there was this like duking it out. I mean, probably like, I think in India where they were influenced by Russia, they were taught like the Wolkenstein equation. And in the England, which is influenced by the US, it taught the Florey-Huggins equation. Huggins was British though too. So anyway, so anyway, nonetheless, you find this paper, if you Google, like you can get, oh, that didn't work. Anyway, I'll fix this link, but what does this say? Wolkenstein, da 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 da. Oh, it's on my page. I know how to fix this. I just need to get my page. Hold on a second. It's interesting. How things like how science kind of, why hasn't it shown my, there, all right, that's good. Let's see, I know how to fix this. I need to get like this part. That goes to that. I need to go back here. It's the same, except this goes, that goes there. This is called, it's like that. That might work. Yeah, all right. So anyway, so he writes this letter. This is a Journal of Polymer Science. Part A is polymer chemistry. So there's A and B. And then there's a letter from Wolkenstein in 1970. So I think this is before, I think Florey got the Nobel Prize in 72 or something like that. So he's reviewing, this is a guy, so this guy copied his book from Russian, you know, and he writes a review of Florey's book. It's a review of Florey's book, and he's really complimentary. He's saying like, oh, it's great, you know, it's really nice, blah, 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 from whatever, Leningrad, which is now St. Petersburg, right? So anyway, it's kind of interesting that, so that's probably how Florey got the Nobel Prize, because Wolkenstein endorsed him, you know, even though he had copied his book, which is like, maybe there's some reason, maybe he paid him, I don't know, something happened there. It's pretty strange though. Eventually they translated Wolkenstein's book, and like you can get the two books and they're the same thing, you know, so it's pretty funny. Anyway, that's an aside, I guess. But anyway, so that's the bond angle, whoever asked that, but that's kind of how you fit that in. I'm not going to go through that. Like, so again, like, if you take a book from 10, 15, or 20 years ago, the whole thing about short range interactions is this. They just go through matrix math. Like it'll be like a whole course on matrix math. So things change. It's like there's a lot more interest in like polyelectrolytes now. And this can't deal with those with this. It's a lot more of a philosophical thing than a mathematical. Anyway, so you'll never see a paper where they're doing this matrix math stuff nowadays. On the other hand, like former head of IBM Almadine, and actually the former head of IBM Research, did a postdoc with Florey after he won the Nobel Prize at Stanford, and then went on. He was a Korean guy. And then he went to Korea and became like the king of polymers in Korea. And the only thing he did was matrix math. Like that's all he did was just like this kind of math stuff from the 70s, I guess. Right. So it's kind of funny how at one point this would be like you went to a meeting and it would be like a whole session, it would be just like matrix math stuff in polymer science. You know, so now it's like not there. So you have to kind of keep in mind that everything you learn today, you just throw out. Like so basically, if you get some feel for what's going on, that's useful. Yeah.
Yeah, I noticed something about the characteristic ratio.
Mm.
Most times they are always greater than or equal to 1.
Right. Yeah.
What if they are less than 1?
Yeah, you can't. It couldn't happen because you have the 1 is like the carbon-carbon bond. That's 1.5 angstrom, 1.54. So you can't make it less than the bond. Maybe you could conceive of how to do that, but no one's figured it out yet. You know? So I mean, it can't be less than that. It could only be 1, and that would be a freely joining carbon-carbon bond, and that can't even exist. And with no excluded bond, with no back, it could backstep even. So it's at least 1.5. We know that from the other thing. That's the minimum it could be. But yeah.
How about the relationship between
the cooling length and the persistent length. Yeah, because generally the cooling length is equals to 2 times the persistent length.
Mhm.
Because it applies
Yeah.
to polymer.
Yes, all right, so it's kind of simple to get that in a sense, right? So you say, so there's a persistent chain model. This is also called a Kratky, I think it's called a Kratky chain also, like an Austrian guy. So anyway, you just say you have a squiggly worm. It's not a chain. It's not none of these step things to it. It's just a whatever I drew, that's what it is. Right. So some chains kind of follow this more than others, right? So if you throw a string on the table, for instance, you can't find a step to it. Right. So it's a little bit more like realistic. So you just take a coordinate system, go to a point, and you can get a tangent of this line that's going through space, like a 3D tangent. That's a 3D chain. I drew it 2D, but it's a 3D tangent, right? And then, so the tangent is the derivative of whatever r within that coordinate system versus the chain, the derivative along the chain contour length, right? S goes from 0 to L. And then that would be the tangent to the chain. So if you want to know what's the end-to-end distance, it's going to be the integral of all those tangents through the contour length to L. Right. So you can get the end-to-end distance. If you want to know, so we have the end-to-end distance squared. I mean, that would be for one chain. On average, that thing would go to 0 if you looked at a bunch of chains, or if you let the same chain wiggle with KT, then this would end up going to 0. But for one frozen moment in time, that would be the end-to-end distance of the chain, right? The integral of that. So anyway, so the dot product of this of two positions along the chain at a position S and a position some other position follows what's called a linear decay function, which is an exponential, which is kind of odd, right? So why would a linear decay function be an exponential? So if you go, like, there's also linear absorption, which is also an exponential, right? So why is it called linear absorption, right? So basically, if the change in the intensity is proportional to the intensity, so with the change in thickness, you have stuff and the light goes through it. If I double the thickness of it, so dx is 2, the drop in intensity is double also. And that drop in intensity is proportional to how much intensity I flooded into it. So if I put twice as much intensity into it, it's twice the drop. That's what it means by linear absorption. There's a linear dependence between the change in intensity that you measure and the intensity you put on, right? And there's a linear between the thickness of the thing, and the relationship is the absorption coefficient, right? So di by I and dx, you integrate di by I integral gives you log, and this gives you just x. So that means you have I is I0 times exponential of blah, 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 right? So that's how you get, when you say it's linear absorption, it's an exponential. So it's the same thing here. You're saying there's the linear change in this correlation is proportional to how correlated it is. The more correlated it is, the bigger the change with something, with the step length along the chain, the contour length. And the factor that relates to that, just like the absorption coefficient is 1 over the thickness, 1 over length, then this thing also becomes 1 over length. All right. So this is a linear change in the correlation function. The linear function exponential. So this is your first guess. Like if you're going to say something changes, you say it changes linearly, then you'd get an exponential function. So it seems kind of odd, like you just pull out of the hat, it's exponential. This is actually the first guess. This is the least number of assumptions you could make about something, right? So anyway, so you use that. So you have, and then you have that this r is that integral. So you want to get r squared, it's that r dot r. It's going to be 2 integrals of this thing dotted against each other. So then you do the dot product. So you have this thing as the exponential. Plug that in here. It's an integral of the exponential. That gives you this mess, right? Which is in the paper this week. This equation's in the paper. So then you say, well, that's a mess, and no way could I relate this persistence length that comes from this exponential decay of correlation with the Kuhn length because this is a mess, and the other thing is very simple. The other thing is R squared is NL squared. And this isn't R squared is NL squared. It's 2LPL. But the front factor here is pretty simple. That's LP. L is LP times L's a constant, but it's LP times NP, the number of persistence units. But L is L, like L here is the same as L here, and here you have LKL, you have LPL, and there's a 2 in front, so it ends up being 2LPL. So 2LP is LK, right? But under what condition? Well, this thing is 1. So when is this 1? When this thing's 0. When is that thing 0? When capital L's infinity. So L is the number of persistent units times the persistence length. So if you have like either infinitely long persistence or infinitely molecular weight, which is more likely, and exponential minus infinity is 0. So then you get 1 divided by infinity is 0. So that thing drops out. So you need an infinite chain for that to work. There's no chain scaling in this. It isn't any Gaussian anything, right? There's nothing about Gaussian. The only thing in it is that if you want to get it to be equal to 2LP's LK, then you have to say it's an infinite chain, which brings you back to this thing. It's like everything is looking at everything's looking at infinite chain here, right? So you have everything is kind of saying like you want to get the biggest chain you can get so you can find this plateau value. So everything has to be C infinity. And then you need to think about what would be Cn, like would this thing change with molecular weight? So what you're going to say something. Oh, yeah, capital L is a contour length. Yeah, it's kind of, I think it's the only symbol that they use for that. So it's N times L, but the N and L can be the chemical unit, it can be the Kuhn unit, it can be the persistence unit.
So capital L is equal to N times what?
N times, all right, so N times, it depends on what, so you have the chain, I can straighten it out, right? So that's L. So L equals how many times L? So it'd be the Kuhn, it also equals the persistence. And it also equals, there's one other, the chemical. So this one's useful because the chemist makes that, and we know that this L for carbon is 1.54 angstrom. And the chemist knows like how many he put in, or you can measure it with chromatography. This thing this is what you actually directly get from neutron scattering or light scattering or X-ray scattering. This week is X-ray scattering. So all these things. So this is going to have a 10 angstrom wavelength. This is going to have a 1.54 angstrom wavelength, which is the same as the carbon-carbon bond length, by kind of a coincidence, I guess, of nature. That's the copper K alpha wavelength that people usually use. In a synchrotron, that's 10 keV energy. Then in neutrons, cold neutrons, they usually get 10 angstrom wavelength, and light is like 0.6 micron for red light, helium neon. Right, so in angstroms, that's 6,000 angstrom. So this, you're kind of looking at different size things with the different techniques, but all of them can potentially give you this persistence length. Kuhn length is kind of rheology. Right, so you can get that from rheology. We showed like the crossover points and things, or the plateau modulus could give it to you. So basically it links together analytic techniques and theoretical chemical synthesis, analytic techniques, and then like simulations all kind of fit together with that. If you look at this number is fixed for everything. So that's kind of a useful number to pull out. So it's pulled out like in this. And the standard way to derive this, which is from the appendix to some book. What book is this in? Too bad I didn't write it here, but this, maybe this is some paper where he goes through it. Oh, Strobel. So this is in the end of the Strobel book, which is online. Gert Strobel. It's in, I think this is just chapter 2. It's in the appendix of a scattering book, I think, this business of this whole thing. I think it's, might be Crackey's book, because it's, huh? I think it's called the Crackey chain model or something. Yeah, but that's just where, that's just something, that's one of my web page. So anyway, this is, anyway, it's called the Crackey model sometimes. I think he has it in the appendix to his book. That doesn't sound right, though. It's in the appendix of some book, but anyway. Yeah. Here.
So, I know you previously told us that stiffness is a function of the bond angle. Is it like an inverse relationship or like a linear relationship?
No, yeah, so for the bond angle, it ends up like this kind of complicated relationship. This is just the 109-degree bond angle. There's also the rotational angle. So there's various angles, right? So you have like, so the card, because it's like a, so each one is going to be like a flagpole flag on a tripod, tetrahedral, right? So it comes in and out, like one comes out, one goes in. And then, so this angle's like, that angle's 72, let's see. That angle's 109 degrees. And then if you put this out, then that would give you the 71 degree that you use in this, like 180 minus 109 would be like 71, right, for that equation. So that's the functionality. If you follow the exact same thing that we did with the don't go back thing, and instead of the 1 over 1 minus z, plug in cosine of 71, then you get this equation comes out. So it's just a function. And it's going to be it'll end up giving a larger persistence, and it'll end up giving a larger R squared than the one that would be just NL squared. So that number is bigger than 1. In fact, I give 1.4 for 109 degrees. For L, so the square of 1.4 would be the R squared difference.
That's the function of that.
Right. Yeah, for the bond. Then there's this rotation. Then there's also a rotation. This thing swings around, and that's the thing about like if you do the Newman projection of that, you're swinging around. This is going down the chain, like eyeball it this way. And then you're looking down and you see in these tripods squished out. So you have the two carbon bonds. That's a rotational angle. And then there's also, and if you go to proteins or anything that's going to be aromatic, you get a dihedral angle. This is easier to draw if I just say dihedral. There's a bunch of things about dihedral angle. So let's see if there's a good one. Well, Wikipedia isn't the best, but it's okay. They don't show it. And I mentioned this because this is also in the paper this week. So, but not for protein, but the dihedral angle comes from the protein. So proteins also have like a conjugated, let's see here, this is a good one. Okay, so you have, this is a protein, so it looks a little bit like nylon. So you have carbon, nitrogens, NH, that's a positive unit in it, and then carbon, and then there's some amino acid, the R, depending on the R, you get lysine and whatever, every kind of amino acid. I think there's like 30 something of them, right? So anyway, see, you're going along carbon, there's this carboxyl group, right, which is negatively charged, that's positively charged. That means, all right, so this is also, this has a resonant structure with this. So this thing can come over here. That means this entire unit is a plane. It has to be planar. So protein's going to be like cards that are connected at the corners, right? And then the cards can like rotate around. That's called the dihedral angle. So it's not the rotational angle here. So there's a bond angle, a rotational angle, and this kind of, when you have planar structures, like conjugated structures with resonant, or structures that have resonant structure, they form sheets. So these sheets can kind of twist around each other. And you can imagine depending on what this, so this is called the alpha carbon, and then the alpha carbon has a different groups on it. Depending on what that group is, this rotation can change, and that makes the protein have a different helical structure in space. So depending on what you stick here, you get different things. So anyway, so that's kind of like, just shows you what a dihedral angle is going to be, this kind of angle. So you measure that with a thing called circular dichroism. So you see how much, because it's going to be helical, it'll rotate light. So that's called, it'll be called a chiral molecule, because you can put it together left-handed or right-handed, and it'll rotate the light left-handed or right-handed. So you can put in like a cross polars and a quarter wave plate that kind of kicks the light into cylindrically polarized light. Then the circular dichroism can measure the amount of like helicity to things. So you use it to, you can make a CD microscope and see like which proteins are where type thing. You can identify these groups of amino acids in it. Anyway, this week they mentioned the dihedral angle, and they mentioned chirality for conducting polymers. It's kind of a mixture of a bunch of different things. But anyway, it's good to kind of know that there is a dihedral angle and roughly what it is. It's basically like, because of the structure of proteins, they're planar structures, and the polarity matters. So because of the planarity and the polarity, that's why they'll form sheets, because this hydrogen will hook up with this carbonyl. So they'll be offset by 1/2 of a mer unit, and they'll just stack offset, 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 and then the whole thing will just be a sheet, like much thinner than a sheet of paper, just atomically thick sheets that form ribbons in space, like beta sheets, basically. So anyway, so that's kind of how. Anyway, they talk about dihedral angle this week in the homework. So I'll talk about that again tomorrow. What are we doing for time here? So anything? I'm not sure. Did you ask that, or someone asked? Oh, you asked about the bond angle. Anyway, there's 3 angles that we're talking about: bond angle, rotational angle, and dihedral angle. Dihedral is mostly for proteins, but it's also in the paper this week. So hopefully that's okay. All right, so what else we got here? All right, so that's that business. All right, so that's how this thing works, right? In other words, and you can only get this from simulations. No analytic technique that can give you this. So this is an advantage of simulations. Before simulations, nobody knew this existed. All right, they knew that there was a molecular weight dependence to the persistence length. That's why they said C infinity, but they didn't exactly know why. So this is clearly what you'd call an N group effect, right? So if you have an N group effect, like the glass transition temperature is also related to this flexibility. The more flexible, the lower the glass transition, so it can flow easier. And the middle part of the chain is going to be more rigid. So it's got a lower glass transition or higher glass transition temperature, right? So the ends can melt before the middle. The ends can flow before the middle can flow. So typically, people talk about that with, I think the ones that I stole it all dead. I put an email to the guys about that thing. Hopefully it'll get fixed. So typically, like you say, TG is like TG infinity plus some number divided by molecular weight. So the 2 is because the chain has like 2 ends, and the dilution of those 2 ends is by the molecular weight. So that if you go to infinity molecular weight, you get the infinite glass transition. So this is like an end effect. End effect equation. Right? I think that's called the Fox equation for glass transition. So you can get this molecular weight dependence to glass transition, you link it back to the molecular weight. All right, so that's kind of your characteristic function for looking at molecular weight dependence. This is the molecular weight dependence in the Kuhn length or the persistence length. So you think, well, maybe you could say like LP equals LP infinity plus some other K KLPs over molecular weight, like would that work for this thing, you know? And that would seem to be. So he's showing, this is kind of what that functionality looks like the persistence length. So he takes this and averages for each chain, right? And then he has, well, this maybe it's a different paper. This is Connolly. And this paper is LE, but also Connolly. So it's like the same group. This one, first author Conley. This is 2005. This is the year before, and it's LE and Connolly's like the, I don't know, they're from Ireland, this group. But anyway, so they were looking at this with Monte Carlo simulations. And then they have this paper is just looking at this stiffness thing, I guess. What's it called? Intrinsic and topological stiffness in branched polymer. So topological would be steric, like add something to the side. So the ultimate of steric is a bottle brush, which they make. I mean, it's commercially made for like viscosity additives to oil, stuff like that. Yeah.
Stiffness plot also for infinite thickness?
No, see, the length of the chain is the bottom axis. That's K. So, and this is steps. So it's step 0, 1, 2, 3, 4, 10, up to 47 or something, right? So these are 47. N is 47. And in chemical, which are beads, they have beads with springs, and they also have a bond flexibility of bending between, or this kind of bending, right? So they have it's 47. So, and then they're all like fixed. Yeah, they don't have infinite, even though it says infinity right next to it. It's kind of confusing, I guess. So this is his. This is the other paper. He's looking at these bottle brushes. So he's making bottle. You can synthetically make these like oil additives. But basically, you can have a low density or a high density. So it would be like really like a bottle brush, like so many. So he's got high density and low density. Then he varies them like the weight of the chain, and he takes like the average Kuhn length of the chain, right? So he finds like, oh, it's got some functionality. And he says, well, he's got this 5-parameter model for it. It's not taking into account like an N group effect. It's just like, oh, here's a function that could fit that, because it looks like it's an exponential. It looks kind of like a Maxwell model relaxation type thing. So he uses kind of a Maxwell model, 1 minus exponentials from the Maxwell relaxation. We have like a model polymer, a dash pot, which I don't think anyone has experienced in their life, but in the 1800s was a popular item when Maxwell was around. I guess a dash pot is like a pot of oil with a piston in it or something, and it just has a drag coefficient. So it's going to be just like the viscosity times the rate of strain, and it gives the force more or less, or the E dot. So it's just a viscous, like a Newtonian viscous element, and this is with a Hookean spring. So K times X is the other force. You have 2 forces in it. One relaxes, one doesn't. Yeah.
What does it mean, like the different branches, like the high versus the low? What is that?
That's what I'm saying. Like this would be low density
okay.
of branches.
Okay.
Yeah, low density and high density.
Okay.
It's like just they have more branches per yeah.
So if there are more branches in a chain, does that essentially then like lower the spring constant and like lower the flexibility?
Yeah, lowers the flexibility. Yeah, so it kind of, yeah, if you're talking about that bending spring constant, yeah, it would increase it because it can't bend as easily. But yeah,
Sorry, what exactly is the backbone width?
that's how many, that's this. So here he has 60, 47. There's going to be like, he has like 10 for some of these. So you can imagine if you took the one that was flexible, right, and then made it short, it would look like the one that's stiff. Like it wouldn't reach a plateau at all. So it would have effectively a lower, because it's taking in more N groups, it would have a lower, persistence length for the short ones. Then as you increase the length, well, eventually you get to the plateau, it should go to a constant if you go to infinite molecular weight. So they're kind of all reaching a constant. And he says, oh, that looks kind of like this Maxwell relaxation model. So just use that equation. Like there's no thought to this, just like there's an equation. It does match the curves. That's great. And there it is. Then he also says like, so this is like called winging it science, kind of. But so you do the simulations and what are you going to do with it? So you have to, so if you get a function, that's useful. So then he says like, oh, it could be a power law. So if you do a power law, yeah, it's kind of a power law too. So you could say, in polymers, everything is power law, so why not use a power law? Then you get this exponent of 1.18, then a prefactor. So then the question is like, what do those mean? He doesn't explain what those mean. It's just kind of like, it's also not some integral number like two, something that you could say was a theory with it. So anyway, this is the problem with simulations. You get to be playing video games and then you start to like think it means something, and then like, well, maybe it does mean something, maybe it doesn't. But anyway, so anyway, if you try to do this idea, which this is using logic, right? It's like there's an equation you could write that would be logic. That's a complete failure. Like if you plot, instead of plotting persistence versus molecular weight, you'd say plot 1 over molecular weight. It's an in-group effect, and you get this thing, which doesn't. It's not good. Didn't work, right? So what is it anyway? So I think we're out of time. So next, I'll just finish this next time. This isn't part of the homework, so I think it's okay. But I don't want to keep going, but slide 57. Yeah.
Link is working.
Oh, okay, let's see.
I think it says like, at least on mine, it's saying like not found or something.
Yeah. Yeah, something's wrong with the link. Sorry about that. I'll
That's
fix
okay.
it. Yeah. The other things are working though,
Yeah,
right?
like the
Yeah.
documents are working, the articles,
All
but
right.
just not
Yeah,
the
sorry. Thanks for pointing that out.
Cool, you got it right. I would use like kind of like producing.
Right, so we'll finish this.
Yeah. Yes. Usually